spares at the front if not. Okay, well, welcome back then. So yesterday I introduced to you some of the basic concepts of machine learning and pattern recognition. In particular, we looked at the problem of classification, and we looked at what we call a supervised classifier, where we show the machine examples of how to categorize data into one or more classes. Like, for example, I might show the machine a picture of a dog, and then it has to figure out if that's a dog or a cat or a lion or whatever. Okay, that's a classification problem. And the idea was that if I showed the machine a training set of data, it could then learn to generalize from that training set by building a model, and then when shown new data, test data, it can make sensible classification decisions on that data. I concluded the talk yesterday by showing you a little bit about how we could build a classifier to determine whether a pixel was a piece of sky or not in an image. And we saw how we could get a reasonable result using that approach. But in fact, the classification wasn't perfect. And one of the reasons that classification was quite poor is because the way we built that model, that ability to generalize, is very simplistic. We just took the mean of the features. In these 2 hours, I'm going to introduce to you the concept of eigenmodels, which are a way to model a training data distribution, not just by its mean, but also by the spread of that data. And we'll see that can give us a more accurate classification performance. So the learning outcomes for this session then are, well, first of all, we're going to just do a little bit of a diversion into some linear algebra, some matrix math, okay, just to make sure everyone's up to speed on that. And in particular, we're going to look at how we can perform geometric transformations in 2 dimensions using matrices. And we're going to look at what we call the active and the passive interpretations of those transformations. And then we're going to use that knowledge to see how we can build an eigenmodel, as we call it, this more sophisticated kind of model of classifying in machine learning. Okay, so right, diversion then, first of all, into linear algebra. Hopefully, many of you have done this at college, or maybe if you took a graphics module, you've done some of this before. If I've got a shape, like this polygon here, in 2 dimensions, so this shape has been defined by 4 vertices that exist in 2 dimensions, they're on these axes x, y, then I can transform that shape into some new location by performing a matrix multiplication on each of those points, each of those vertices that makes up that shape. So, for example, if I had this polygon here, and this particular point here, this particular vertex had coordinates 2, 3, this means 2 on the x-axis, 3 on the y-axis, then I could place those coordinates here, okay, and then apply some matrix transformation to it. In this case, this is a matrix that will scale that point by a factor of 2 away from the origin of the space, and that will give me some new location of that point, which in this case would be 4, 6, because it's multiplied everything by 2. Okay, is everyone happy with that? How many people have seen this before? Okay, not everyone, about half. Okay, so it's worth doing this recap then. Okay, so first thing to note is that in computer vision, when we are working with points in a space, we normally write them in its column form, okay? Sometimes maybe if you've done some computer graphics, you're used to seeing points represented as a vector, but in like a row form. We're working with them in a column form, okay? And what we're introducing here then, or perhaps recapping if you've seen it before, is this matrix multiplication framework, whereby if I take every point, each in turn, of our shape, of our polygon, I'm going to pre-multiply that point by this 2 by 2 matrix, which defines the kind of transformation I want to do. In this case, it's a scaling matrix, it scales the point by a factor of 2, to give us each of the points' new location. Yeah? Everyone happy with that? Okay. So in this framework, we can do scaling. If I have a matrix here that has basically just values down a diagonal, then that matrix is a scaling matrix. This value here is the multiplier I want on the x-axis. This value here, the multiplier on the y-axis. You can see that's the case because, just to recap again if you've forgotten, when we do our matrix multiplication, what we're doing is we take our point here, we take our matrix, we take the top row of the matrix, turn it onto here, and then we place multiply and then add up to get our result for here. So in this case, it's 2 times x plus 0 lots of y. So x prime here is 2x. yeah? And then to get the y prime, it's this row here. 0 lots of x plus 2 lots of y gives us our y prime, okay? So clearly, if I do that to every point here, it's going to scale the shape up on the two-dimensional axes. We can do other useful things in this framework. So instead of having my matrix here, like a scaling matrix, I could have a matrix that looks like this, where I've got cos theta, negative sine theta, cos theta. That is a rotation matrix. So if I were to define my theta to some value, like, I don't know, 45 degrees, okay, and then I was to then take that 2 by 2 matrix, which would just have constants in it now, and pre-multiply every point, every vertex of that polygon by that matrix, then I would get a bunch of new positions for those vertices, and the shape would have rotated 45 degrees, in this case anti-clockwise, about the origin. Okay, so the point of this is, I guess, just a recap really. I guess many of you will have done this in school, but basically we can say that each of these points is moving under this transformation to a new location, and that's what we call the active interpretation of these transforms. Okay, is everyone happy with that? Okay, great. Well, if you put 180 degrees into here, what's going to happen? Well, your cosine is going to be 0. Yeah. They're going to be minus 1. So yeah. So in my sine cosine might be embarrassing. So yeah. Okay. So then these values then they're going to be 0, and then this is going to be exactly your negative value, and it's going to be positive. So it's going to change the sign on those equations. So yeah, okay. So this is like a useful framework. In computer graphics, we use this all the time as a general framework for performing linear transformations, like scaling, rotating, shearing shapes. Okay. The one thing you can't do in this framework is do translation, or shifting of the shape about. Okay. There's no way that we can add some constant amount to one of these values without it having an effect on the other value when we're constrained to just doing a 2 by 2 matrix multiplication. So just for example, as I said, these values here for the scaling matrix, this is a scale factor in x, this is a scale factor in y. These don't have to be the same thing. If they're 1, the scale factor is 1 for both, and you can see that that's the identity matrix. Okay, remember the identity matrix is the matrix where we have 1s all the way down the diagonal. It's the do nothing matrix, no operation. It's the same as multiplying by 1 with scalars. Okay, you could imagine then that would just give us the same point out. And you could have different values for x and y, and that will stretch your shape in different directions. So here's a question. How do you think you might go about scaling a shape not just along the x or the y axis? How about scaling it along an arbitrary axis? Does anyone have any suggestions about how you might do that? The only controls you've got in this matrix are the amount to scale along the x-axis and the amount to scale along the y-axis. So you can stretch the shape out this way or stretch the shape out this way. What if you wanted to stretch the shape out this way to make almost like a kite shape along it? Yeah, absolutely. Thank you. Yeah, that's right. So what you can do is perform what we call a compound matrix transformation. Okay. So what you can do is rotate this axis that you want to scale along so that it's aligned to, for example, the x-axis. Yeah. Then, having done that rotation, you do your scaling along the x-axis. So this would be some value here and then 1 here. Yeah. And then you would do the inverse rotation back. Does that make sense? Okay, so hopefully none of this is new to you if you've done a bit of geometry before in maths. So here's that equation then that I've just described. What we've got here is a point that we're applying some rotation. Remember, this matrix here is performing a rotation anti-clockwise about the origin. So you're going to have to kind of come up with some appropriate value of theta that will align this axis to the x-axis, which is, would be, I guess, rotation by negative theta here. And then having performed that rotation, let's suppose we forget this part of the equation here. Okay, if I just do this, this is going to rotate this point, or the whole space, to give me new positions here. But then instead of just outputting the result, I'm then going to pre-multiply the result by this matrix here, which is some scale by some arbitrary amount along the x-axis. And then finally, I'm going to pre-multiply the result of that by the inverse of the rotation matrix. Yeah? To undo that rotation and take the space back to where it was. Does that make sense? So one interesting thing to note here, this matrix then, of course, is the inverse of this matrix. Okay, can you see how it looks very similar, but the sign has changed, the sign on the sign has changed? Okay, so it turns out that this matrix here is an example of what we call an orthonormal matrix. Okay, what that means is, if you look at the columns of this matrix and interpret them as vectors, those vectors are of unit length, and they're also normal. That means perpendicular to one another. Yeah? So this, if the matrix has the property that its component columns, its component vectors are orthogonal and they're all of unit length, we call it an orthonormal matrix. If your matrix is orthonormal, then you can do a special shortcut to compute its inverse. You can just transpose the matrix, which basically means flip it on its diagonal. Transpose the matrix. Hopefully you remember that from some vector maths. So you can see here, that's the inverse of that matrix. It's important we remember that trick of how to invert a orthonormal matrix, because later on in the second hour, I'm going to be talking about that. Okay. Right, is everyone okay with this? I'm happy to go into that in any more detail. If you've got questions, maybe you haven't done it before, or you've got a bit of a rusty area, I can take questions on that. Yeah? Okay. So, the other thing I'd like to revise, and again, hopefully this is a concept you've encountered before when you've done some college maths, is the concept of what we call a reference frame. Okay? When we talk about the reference frame, defined by a set of by a space, like this space, this two-dimensional space here, okay, the reference frame refers to the origin of the space, where the origin of the space is, and also the direction that each of the axes points in. So concretely, if I've got a point here in this two-dimensional space, a location 3, 4, okay, then I'll write that point, in this form, 3, 4. But what that actually means is I've taken 3 steps along the x-axis and 4 steps along the y-axis. In other words, I've taken 3 steps in this direction I, yeah, where I just is 1 unit step along the x-axis, and 4 steps in this direction J, okay, which is pointing 1 step along the y-axis. We're used to, when we plot points in 2 dimensions, we're used to I just being 1, 0, and J being 0, 1, right? We're used to this being 1 step for every unit on the x and the y-axis. But there's no reason that I and J have to be defined this way. They could be defined, as a pair of vectors, any pair of vectors that are anti-parallel, yeah, that aren't pointing in the same direction, that could be the values for these vectors. So these vectors I and J determine the directions we step in when we move along each of our axes, and we call each of these a basis vector, and together they form the basis set of the space that we're working in. Yeah? Okay, so I and J are the basis set of this space. We're used to that basis set being 1, 0 and 0, 1, but they could be anything. Yeah? Everyone happy with that? The basis set and the location of the origin in the space form the reference frame, okay, that this point exists in. Is everyone happy with that terminology and way of thinking about the space? Obviously, I've shown it in 2 dimensions here, but the whole concept would also generalize to any number of dimensions. Yeah? Imagine we've got a K for 3 dimensions and so on. Yeah? Everyone okay with that? Okay, do interrupt me at any time if you've got any questions. Okay, so I asked the question then, what would happen then if we did choose a different I and J? What would happen, for example, if I chose an I that was 2, 0 and a J that was 0, 2? What would my coordinates 3, 4 mean in such a space? Yeah, it means that basically I'm going to move twice as far for every step I take in the x and the y direction. So the coordinates 3, 4 defined in a reference frame where I is 2, 0 and j is 0, 2 actually means it's going to be at location 6, 8, as you correctly said. Yeah? So to be a little bit more formal, when I say it actually means it's 6, 8, what I mean is a point 3, 4 defined in the basis set 2, 0, 0, 1 has the location 6, 8 in the root reference frame. The root reference name is the name we give to our reference frame we normally work in, which is where I is 1, 0 and j is 0, 1. Okay? So when I asked you that question, you were converting the point 3, 4 defined in an arbitrary reference frame into a location 6, 8 in the root reference frame, the frame we normally work in. Everyone okay with that terminology? Okay. Right, so yeah, that's the point I was just making. Okay, so let's look at this transformation then that I showed you on the very first slide of the lecture in a different way. Let's suppose that I don't view this transformation here as a transformation that is basically being interpreted in the active sense, which, remember, is the sense in which we say, okay, we've got a point 3, 4, and this matrix here, which is our scale factor 2 scaling matrix, okay, a uniform scale by a factor of 2, we're not going to view it as that this point is being transformed by this matrix to a new location. We're going to view it in a different sense. We're going to view it in what's called the passive interpretation. And in a passive interpretation, we're going to consider this matrix here, this 2 by 2 matrix, not as being some transformation on that point, but as the matrix that defines an arbitrary reference frame. The reference frame where I is 2, 0 and j is 0, 2. And when I perform this matrix multiplication, what I'm going to do is I'm going to say that it's casting this point 3, 4 that's defined within this reference frame into the root reference frame. Does that make sense? So the maths hasn't changed. I've still got a point, x, y, being pre-multiplied by a matrix 2, 0, 0, 2, the scaling matrix by a factor of 2, to get to a new point. But instead of thinking about it in the active sense, which is this matrix moves this point, I'm going to say actually what this matrix is doing is casting a point that's defined within its reference frame out into the root reference frame. Does that make sense? The passive interpretation. Okay. Any questions on that? So, in other words, what I'm saying is that this matrix here, M, is defining the basis of this reference frame. This point here, P, I'm going to use this notation subscript M to say that this point P exists in the reference frame M, which is defined obviously by this matrix M. And when I do this multiplication, I'm moving to point P subscript R, where R means the root reference frame. I'm casting the point from an arbitrary reference frame into the root reference frame. And I can do the opposite. If I've got a point in the root reference frame, which would be my 6, 8, for example, I can pre-multiply it by the inverse of this matrix to cast it into that arbitrary reference frame that's defined by M. Yeah? Does everyone see that? So this idea of having a matrix M that defines the root reference frame, I can take its inverse to go the opposite direction. Yeah? And remember, if we're really lucky and that matrix M is orthonormal, which it's not here, okay, you can see that's not orthonormal. These vectors are orthogonal, but they're not of unit length. They're obviously of length 2, okay? Then we could just take the transpose of that, but clearly that's not the case here. That's just a little reminder. Okay. So, this slide then is just a recap then. This matrix multiplication can be considered to be, the maths doesn't change, but we can just interpret it as being an active or passive transformation. I won't repeat it the third time. Okay, so here's a little question for you then to work on for a couple of minutes. Okay, if I've got a point that's defined in reference frame D, so a P subscript D, and I've also got the matrix D, yeah? And I want to express that point in some other reference frame that's defined by a matrix E, can you write down the expression for doing that? So the quantities I've got are PD, which is my point, in some arbitrary reference frame D, which is defined by the 2 by 2 matrix D. So I've got PD and I've got D. And I've also got E, which is defining another arbitrary reference frame. And I want to cast PD's coordinates into the reference frame E. In other words, I want to find PE. Can you write down an expression for PE? Have a go now, 2 minutes. Feel free to talk to your neighbour if you want. Let me give you a hint while you're doing that. You want to think about how you can cast point D, point PD into the root reference frame, and then how you convert from the root reference frame into the E reference frame. All right, does anyone want to give me an answer? Yeah. Well, yeah. Right, thank you. That's the correct answer. So you would get your point in the root reference frame PR by pre-multiplying point PD by D. So PR would equal DPD, yeah? And then to go from PR, your point in the root reference frame, into frame E, you would go, you would pre-multiply by the inverse of E, as you put it, E to the -1, but it's not actually E to the -1, it's the inverse of E. So yeah, so exactly that. We go from PD into our root reference frame by pre-multiplying by D, and then from the root reference frame, we go into frame E by pre-multiplying by E inverse. Because remember, it's the inverse that takes us from the root into the arbitrary frame, yeah? So, substituting in here for PR, this is our expression here. PE is equal to E inverse D PD. Right, everyone okay with that? Any questions on that at all? This is an important concept to remember when we talk about eigenmodels, which we're coming to next. Right. Okay, so let's think back now to the last lecture. And in the last lecture, we were talking about this problem of classifying pixels as being sky or not sky. So we were taking a picture like this, and we were going through every pixel in turn. And if you remember, we were looking at the RGB values of each pixel. So it was basically each pixel was having 3 features measured about it, the red, the green, and the blue. And we were considering that pixel then to have a point in a 3-dimensional feature space. And then having trained up a model, which was basically the mean average of a bunch of training pixels of sky in that feature space, we were measuring the distance between every pixel and that average, that model, in order to, and thresholding that distance to make a classification decision. Yeah? So this was our training data. It's a little patch of sky we got from somewhere. We were looking at every pixel here and measuring its R, G, and B, which gave it a point here in our feature space, 3-dimensional feature space. Okay? And then, given a new pixel, have the animation, a test pixel, we were measuring its distance to that mean and thresholding that distance. Everyone remember? It was only yesterday. Okay. Now, implicitly, that means that we were defining a decision boundary, yeah, at that threshold value. Yeah? So if we were thresholding at 0.2, which I think was one of the examples I gave yesterday, okay, then basically we've got a sphere of radius 0.2 centered on that mean, which defines our decision boundary. Everything outside it was not sky, everything inside it was sky. Okay? However, if I were to load up MATLAB and plot these points in 3 dimensions to inspect the distribution of those points in 3-dimensional space, I get a plot that looks like this. There's my mean of those points, and these are my points. Now, as you can see, the distribution of these points in the feature space is not spherical. It's sort of ellipsoid, it's elongated like a rugby ball. Yeah. So it's actually not a good idea to be using a spherical decision boundary here. What we want is a decision boundary that matches the shape of the training distribution. So clearly, this is a deficiency in the way that we're modeling our distribution, our training pixels. So, so the takeaway message is that we're assuming 2 things about this distribution. We're assuming it's unimodal, which means basically it makes one cluster in the space. There's one sort of sensible mean average for it, which is true in this case. But we're assuming also it's uniformly distributed about the mean, which is actually not true. We say the distribution is anisotropic. If it was uniformly distributed, we call it isotropic. Okay, so this is actually then what our training data distribution looks like. Here it is, about that mean we calculated, and we can immediately see a problem here. If I've got 2 pixels, 2 test pixels from my image that I want to classify, let's suppose one of them lands here in the feature space and one of them lands here. Both of these test points are the same Euclidean distance, the same L2 distance from the mean. But one of them is so close to that training distribution, it might as well be part of it. And the other one is super far from that distribution. It's clearly not part of it. But by thresholding, all we're doing at the moment in our simple system is we're thresholding on this distance. So can a spherical decision boundary fit in this situation? No, not well. Yeah, there's no good spherical decision boundary I can fit. What I'd like instead is an ellipsoid decision boundary, so that this point here, that clearly is sky, is inside the decision boundary, and this pixel here that's not sky is outside the decision boundary. Everyone following? Any questions on that so far? So that's our motivation. So we're going to look. Now. We're building up to looking at a new kind of model that's not just based on the mean, but also based on the spread or shape of the distribution. So when we talk about a distribution of numbers, let's suppose we're just talking about a one-dimensional distribution of numbers. So these are just points on a number line. Okay. In this one-dimensional sense, the way we're used to talking about the mean and the distribution of those points is by talking about the mean average. Imagine I've got a number line, lots of points along a number line. If I want to get their mean, I just compute their average, that's the middle of them. But if I want to talk about the spread of those points about the mean, then I'm really talking about either the standard deviation of those points about the mean, or more commonly, I talk about the variance of those points about the mean, which is just simply the standard deviation squared. Okay, it's convenient to talk about the variance because it's always positive. Okay? So in one dimension, if I'm talking about a distribution of points on a number line in one dimensions, I talk about the mean and its variance. Okay, but if we're working in more than one dimension, as we almost always are in machine learning, then actually we're working in what we call an n-dimensional space, some high-dimensional space. It's still super easy to calculate the mean. It's just the average of each feature, yeah, to calculate the mean. But if we want to start talking about the variance of those points, there's actually not a single number that we can come up with that describes the spread of those points, because it's a spread that's occurring in a multi-dimensional space. Another way of talking about that is imagine this room. Okay, well, you don't need to, you're sitting in it. Okay, the room is three-dimensional. Okay, so imagine there's a cloud of points going all the way down the middle of this room, from that clock all the way up to this board in like a big, long sort of ellipsoid shape. Okay, if I stand here and look at that spread of points, it looks quite compact. But if I stand all the way over here and look at those points, I can see it's actually quite spread out. So the position that I view those points from defines my perception of the spread of that data. So I need to come up with a quantity that is sort of invariant to the direction I'm looking at the points from. We call this quantity the covariance of the data. The covariance of data is like a generalization of this concept of variance in one dimensions to n-dimensional space. It's expressed as a matrix quantity. So if I were working in 2 dimensions, the covariance is expressed as a 2 by 2 matrix. If I'm working in 3 dimensions, as I am in this example, the covariance is expressed as a 3 by 3 matrix, and so on. Okay? So, now get into the maths of it. In 1 dimension, I hope everyone is familiar with these 2 equations. If I have some data, let's index that data by subscript I. So x is my data points, x1, x2, x3, all the way up to xn. Yeah, so I've got n data points. If I want to calculate the mean, which we normally write as mu, then I just simply sum up those data points and then divide by the number of data points. If I want to calculate the variance, and we normally write the variance as sigma squared, because sigma is the symbol we normally use for standard deviation. The variance we just should normally write is just sigma squared, so that's just the notation for variance. In 1 dimension, all we do is we take each of those, having computed the mean, we take each of those data points, subtract the mean from it, square it, and then sum them up. And then again, we divide by the number of data points. That's our equation for calculating the variance. If I'm working with multi-dimensional data, then my data, my xi, they're no longer just numbers, what we call scalars. Okay, each of these points is a vector in itself. So if I'm computing the mean, actually the equation doesn't change, but we just have to bear in mind that these points now are vectors. These points in our high-dimensional space are vectors, so this mu is a vector quantity. But if we want to calculate the covariance, then what we do is we create a matrix of these data points, where each column in this matrix, I'm calling this matrix X here, each column in this matrix is a point, from point 1 all the way up to point n. I subtract then, having computed this mean, I subtract that vector from each of these columns. I'm going to abuse this notation for simplicity and just put x minus mu, but of course, you know, we wrote that in MATLAB or something, you know, this wouldn't work because this is a matrix and this is a vector. We're just going to abuse this notation, which simply means let's take away this vector mu from each of the columns in here to create a mean subtracted set of points, again as a matrix. And then what I'm going to do is take what's called the outer product of this matrix. So I'm going to take this matrix, having subtracted the means from the points, and I'm going to multiply it with a matrix, well, basically this matrix transpose, which is what this superscript T means. Sometimes you use a little prime, but I use T. And so that's going to be basically 2 columns, okay, where every row there is a mean subtracted point. And that's going to then give me a square matrix, as I say, which is of D by D matrix, where D is the number of dimensions we're working in. Does that make sense? Okay. So what is the meaning then of these entries in this matrix? Well, if we were looking down the diagonal of the covariance matrix, then basically each of those numbers down the diagonal corresponds to the variance of the data along that respective axis of the space. So if I was working in 2-dimensional space, x and y, okay, my feature space was 2-dimensional, then if I looked at location, you know, the top left location in my 2 by 2 matrix, 1, 1 if you like, then that is going to be a value that corresponds to the variance of the data as if I were looking down the x-axis. Yeah? In other words, if I projected that data, as we call it, onto the x-axis. Similarly for location 2, 2, so the bottom right value is going to be the variance along the y-axis. Yeah? The off-diagonal elements of that matrix refer to the variance of that data down one axis as if it were viewed from the other axis. Yeah? In other words, the data projected onto the other axis, the variance in that dimension. Does that make sense? The takeaway message then is that to talk about the mean and spread of data in a high-dimensional space, we have to calculate the mean by our usual method, but we have to express that spread of that distribution using this covariance matrix. Yeah? So this then is the process by which we calculate it, just summarized. We have our data points, our set of data points x, which we've indexed here by a subscript. That's meant to be a subscript x1, x2, x3, which decompose into these numbers that are the elements of that, each of those vectors. We're then going to calculate the mean, and then we're going to produce a mean subtracted version of this matrix, take its outer product, and crucially we have to divide every element in that covariance matrix then by n to get this C here, which refers to our covariance matrix, which in this case, because these points are two-dimensional, is a 2x2 matrix. That make sense? All right, so what I'm going to do, actually I'll do it. No, I'll do it now. A quick demo in MATLAB. Oh, my machine is. Windows has updated me, that's good. I like to be updated. I do know I'm in Windows 7, I'm not running Windows 10, obviously. Right. I'm afraid this isn't going to lecture capture. Oh, it might, but via the camera. So let's see. Right. Okay, so let's just make a quick demo here in MATLAB then to show you what I'm talking about. Can everyone read that, or do I need to turn the lights down? Maybe I'll turn it down. It's a little bit better. Okay, so I'm going to create a two-dimensional distribution now. Okay. So let's create a distribution of 1,000 two-dimensional points. Okay, there they are. All right, and what I'm going to do is I've called those x. What I'm going to do is artificially scale the x dimension of those by some large factor like 5, for example. Okay, now let's plot that distribution of points. So let's see if it does that. Okay, so there's my distribution. Let me just make the axes equal size. Okay, so you can see clearly that random distribution of points there has been stretched out in the x direction. Yeah, it varies more in the x direction than it does in the y direction. Okay, so now what we're going to do is calculate its mean and covariance. So the first thing we need to do is calculate its mean. So the way we calculate its mean is, well, we just average the first row of numbers to get the average in the x direction, average the second row to get the average in the y direction. Okay, so let's just do that using the mean command. Okay, so there's my mean. Okay, those points. Let's plot that. Okay, star. Let's do black star. Okay, so you can see the mean there. Now what we're going to do is calculate that covariance matrix. And remember, that covariance matrix will be a 2x2 matrix because we're working in 2D. So how do we calculate the covariance matrix? What's the first step? Well, actually, I've done the first step. It's getting the mean. What's the second step? Subtract the mean from every point in x. So let's make a matrix. Let's call it P this time. And it's going to be x minus the mean. And the way we do that in MATLAB is like that. That's just replicating that vector mn 1,000 times, so it's the same size as x, and then subtracting the two. So if I were to I'll just type P there, you can see that there's some negative values there. They've all had the mean subtracted from every single column there. Now, the next step then is I'm going to take the outer product, so P times P transpose, which is usual apostrophe in MATLAB, and all of that divided by the number of points, which is 1,000. Okay, so that is my covariance matrix for that data. Okay, and you can immediately see that we've got a larger number here than we have here. Yeah? Okay, which means the data has a larger variance in the x direction than the y direction. I'll come back to this demo later on. Okay, so I was just implementing there in MATLAB then that bit of maths. Okay, so finally we come to this interesting model called the eigenmodel, and in order to build it, we have to factorize the covariance matrix, except when we're working with matrices, we don't call it factorization, we call it matrix decomposition, but you can think of it as basically like factorization for matrices. And what we're going to do is factorize or decompose this matrix C into U and V, such that if I multiply U and V and then the transpose of U together, I recover my C. Okay, so I'm factorizing C into U and V. Okay. Now in this example, remember, it's not two-dimensional like I showed you here, it's three-dimensional, the three-dimensional space here. Okay, so remember this is our pixel value space, RGB space. Okay, so this C is 3 by 3, we're working in three-dimensional space, and it turns out that this will give, this factorization, this decomposition will give us a U and a V that are also 3 by 3 matrices. So all these matrices are D by D, where D is the number of dimensions you're working with. Okay, U is a matrix that contains columns, each of which have a special property. We call those columns in U the eigenvectors. V is a diagonal matrix, okay, which means it just has values down its diagonal, zeros everywhere else, that contains some things called the eigenvalues. Okay? And these eigenvectors and eigenvalues describe the shape of that distribution somehow. How do they describe it? Oh, I should just point out, the way that we calculate this decomposition, we don't need to go into on this course. It's via an algorithm called eigenvalue decomposition. Maybe you studied it in further maths, maybe you didn't. It doesn't really matter. In MATLAB, there's just a command called I, which calculates it. That's as much as we need to know for this module. Okay. Very happy to talk to you about that afterwards. If not, it takes another lecture though. Okay, so let's have a look at U and V and their formats. If we take a look in U, as I say, the columns of U are to be interpreted as vectors, and we call those eigenvectors. Eigen, by the way, is the sort of stem word for characteristic in German. So what this means is got characteristic vectors, okay, for distribution. The eigenvectors point in the directions of variation of that data distribution that we built C from. Usually, the algorithm that computes them will order these such that the first column in this matrix is what we call the principal eigenvector. That's the eigenvector that points in the direction of greatest variation of this data. So in the example where I have my cloud of points down in a sausage shape, in an ellipse shape down this room, then the principal eigenvector would be pointing down this room from the board all the way down to the clock. Yeah? Okay. The direction of the eigenvector is kind of undefined, so it's equivalent to have an eigenvector that's pointing in this direction or this direction. Yeah, where in this case the red is meant to indicate the principal direction of variation of this point. Okay, it's the direction of greatest spread of these points. The second eigenvector and the third eigenvector, in fact all of the eigenvectors are orthogonal. They're all perpendicular to one another. This second eigenvector points in the direction of second greatest variation under that constraint. The third, in the direction of third greatest variation. So the eigenvectors then define, if you like, a basis set that is aligned to the spread of the data in that distribution. Yeah? Yeah. No, absolutely may not. This is very important. Thank you for the question. We have a space here defined by 3 vectors, X, Y, and Z, or in this case, it's red, green, and blue, wasn't it? These vectors here are orthogonal to one another, but they will be at some arbitrary rotation within that space. They almost certainly won't be pointing down these directions. They'll be pointing at some other direction. So let's suppose, give you a concrete example. Let's suppose then, actually I'll give you a concrete example in just a moment. Let's just briefly talk about what the eigenvalues are. Each of these eigenvalues down a diagonal corresponds to an eigenvector. It describes the variance or spread of the points along each of the respective eigenvectors. So the eigenvalue that is largest, okay, corresponds to the principal eigenvector, okay? So as I say, normally the algorithm that produces these will sort these in some way. Usually it's such that this is the largest to the smallest, but actually we shouldn't talk about the largest or smallest eigenvectors because the eigenvectors are all of unit length. It's the eigenvalues that describe the variance along each of the directions defined by the eigenvectors, okay? So, concrete example then, here I am in a room, it's three-dimensional. Let's say that my room is defined by axes X, Y, and Z up the wall there. Okay, so that's the origin of my space in the corner there, and that wall is the X, this is Y, this is Z. I've got my data distribution down the middle of the room. I've calculated the mean, which is right in the middle of it, and I've calculated now the covariance of that distribution to get a 3 by 3 matrix, and I've performed the eigen decomposition to get U and V. If I were to look in my U, I'd have 3 columns. The principal eigenvector would correspond to the points down this room, down the centre of this room. The second eigenvector perhaps in this direction, the third perhaps in this direction. Okay, but you know, that distribution might be in any direction in the room. So those 3 vectors will be oriented at some arbitrary rotation aligned to the data with respect to the axes of the space. Yeah, and together with the mean of that data distribution defines a reference frame. The mean is like the origin, and these are like the basis vectors. It's a data-dependent basis set and reference frame from the data. Yeah, does that make sense? Okay. Right. I mentioned before that the eigenvectors are all orthogonal to one another, and also mentioned that they all have unit length. So we note that this matrix is an orthonormal matrix. That's important, we'll come back to that. Let me just give you another concrete example. Let's suppose here, along this front here on this desk, okay, I've got a distribution of points. I've scattered points all the way on top of this, all the way along here, okay? I'm going to calculate now my mean of the points. They're going to be pretty much right here, in the middle of this long set of points that have been distributed on this desk. I'm now going to calculate the covariance, and from it, the eigenvectors and eigenvalues. The principal eigenvalue will point along this desk in the direction of greatest variation, because that's where most of the points are scattered. The second eigenvalue is going to is going to point orthogonally on top of here, and the third eigenvector is going to point directly up. Now, the points have been scattered along this two-dimensional surface embedded in this three-dimensional world. So this third eigenvalue is going to be 0 because there's no variation in this direction. It only varied in that direction and that direction. Yeah. So it's quite acceptable for these eigenvalues to be 0, but there will always be 3 eigenvectors and there will always be 3 eigenvalues because we're working in a three-dimensional space. Everyone happy with that? So we'll come back to the significance of when we do have 0 eigenvalues later. So, demo. So I'm going back to my MATLAB now, and there's my covariance matrix C that I calculated from that distribution previously. I'm going to now decompose that C using the eig function, which does that eigenvalue decomposition. It's going to give me a U and a V. The U contains 2 columns because it's two-dimensional distribution, remember? So our covariance matrix and our U and our V are all 2 by 2 now. Look at these 2 columns of U. they describe the first of these. Oh, sorry. So, and look at V. It's diagonal. So let's look in V. Let's figure out where the largest value on the diagonal is in V. It's this one here. So this corresponds to this second column here. So in fact, actually, this algorithm is giving us, this is our principal eigenvector here. And look at the way it's pointing. It's pointing at basically -1, 0. Yeah? So this is telling us the greatest direction of variation is in direction -1, 0 in the space, i.e. it's aligned to the x-axis. Notice an equally valid response would have been 1, 0. So there's an ambiguity there that the algorithm that computes these things gives us. Okay? The second eigenvalue is going 0, 1. So it's pointing on the vertical, which is the only other direction it could have pointed, because they're always orthogonal to one another. And these variances here actually are equivalent to the variances we saw here. But what if I were to rotate those points? Well, why not? Let's just do it. So let's make a rotation matrix. So we're going to rotate by 45 degrees, or pi over 4 radians. Let's make a rotation matrix. Cos theta, remember, minus sine theta, cos theta. There it is. Okay. Let's take those points P, and we're going to make something called P2, which is just the rotation of those points under that matrix. So there's my P2. Shall we plot it? Actually, let's get rid of the previous plot. I've done this to the mean subtracted points just for convenience. It's P2, isn't it? Let's plot this off. Oh, oops. Okay, there's my points. I rotated them 45 degrees using that matrix. Now let's compute that C, that covariance C. See how it's changed? Let's do the decomposition to calculate the U and the V. Okay, now we still see our eigenvalues basically what we had before. We've still got these two numbers, they're pretty much the same as they were before. But look how the eigenvectors have changed. The principal eigenvector now is pointing basically along the line x equals y, and this is orthogonal to it. So can you see how this process has allowed us to determine from the data distribution not only where its centre is, which is obvious, just calculate its mean, but also its principal directions of variation and the amount that the data varies in each of those directions. Yeah? Right. Any questions on that at all? Yeah. Well, okay. So what is the intuition of the ordering? What are the order of these vectors? Oh, do we want to go into this? So no, it's a fair question. Okay, so actually, right, because this matrix here U, okay, it's not necessary really to understand this, but because this matrix U consists of it's orthonormal, consists of vectors that are all orthogonal and normal to one, or orthogonal and of unit length. This is actually a rotation matrix. Okay, and U transpose we took is the inverse of that matrix because it's orthonormal. U transpose is the same as its inverse. V just has entries down the diagonal, so we can consider that to be a scaling matrix. So actually, this C is like it's saying take your data that's aligned in some arbitrary direction, rotate it to the root reference frame, scale it, and rotate it back again. A bit like that scaling on the axis I showed at the beginning. And that gives us our C. So that's the intuition behind it. So, oh yeah. Correct. Yeah, the principal eigenvector points down the direction of great speed. Pardon? Yeah. second column. Right. Okay. The process by which we calculate this eigendecomposition, I'm not going into this course. I used to have it in this course, so I thought, anyway, we don't do it anymore. Okay. The process for doing this, you have to basically, there's a step in it in which is kind of arbitrary which of two equations you solve, and this algorithm just solves, built into MATLAB, just solves them in a particular order that means that these things end up being stacked in this way. It doesn't really matter what order these vectors are in U, because we're looking down V to basically look for the largest value. So the value in here, the second one down the diagonal, the 2, 2. So this value corresponds to this column. This value corresponds to this column. Yeah? The order that these appear, and therefore the order that these appear, in what's returned, is an artifact of the developer who coded this function. Right? We don't care. What we do is we look in here at the values, and we look for the corresponding column in here. Okay? It's actually quite unusual to see them ordered in this way. Normally people order them the other way. It's just the way MATLAB is doing. But there's a lot of funny things about MATLAB. Right. Vectors and the eigenvalues, basically mu, u, and v. We call that collectively the eigenmodel that we've built from the data. It defines a data-dependent reference frame for your training data distribution. Okay? The process for computing it, just to recap, is take the data points and stack them in a matrix in column form, calculate the mean of those points, calculate a mean subtracted matrix, and then take the outer product of it, dividing by n to get your covariance matrix, and then decompose C such that C equals U, V, U transpose to get U and V, which then contain your eigenvectors and eigenvalues respectively. It is super, super important you remember this, yeah? Because this underpins a lot of what we talk about in subsequent lectures. So in the labs, you'll get practice of doing this manually, but I also give you a function that does it too. This process of building an eigenmodel is sometimes referred to as performing principal component analysis, or PCA, on the points. Okay? In other words, it's principal component analysis, basically just working out which directions your data varies in within its feature space. You can see that it's doing that. So when we say, oh, I did PCA on the points, as I'll say frequently, we're doing this. Yeah? We're calculating an eigenmodel from the points. All right, so I think it's time for a break now for maybe 10 minutes. But in summary, I went through initially in this lecture a recap of the linear algebra, particularly focusing on the geometric interpretation of matrix transforms and how we can think about those in the active and the passive sense. I then went on to describe this process of performing principal component analysis, in other words, calculating the mean covariance and decomposing the covariance of a data distribution. I haven't yet explained why this is relevant to this discussion. That's coming in the next hour. Okay, let's send there. Come back at 10 past. Thanks very much.